Tassinelli. Thought there was an I in there. All right, great. We still have breakfast tacos. We got to keep selling them.
Is this working now?
Yeah.
All right. That's better. What's this? Okay. All right. Well, good morning. My name is Matthew Benson, and I'm one of the owners of Windhover Labs. You might be asking, like, what does this have to do with all the other work here, which is mostly going to be space flight. My experience, so I've been working for 16 years on space station, on Orion, I think almost all the manned vehicles. And just recently, I took an interest in CFS and with drones, and this was, and I love to write. I like to write software, and so this is an easy way of getting more experience with CFS and with space flight, or flight software, is to write flight software for drones. So I started this company, which is Windhover Labs. We're a small company. This is actually half of the company right here. And I'm going to hand this off over to Casey. He's a much better orator than I am.
Can you hear me okay?
There you go.
So as Matt said, we are a Houston-based startup that develops flight software for drones.
Hello?
Okay, all right.
A little bit this way.
Are you able to hear him?
Can you hear me okay? Is that better? Okay, that's better. This presentation is an overview about the past 2 years of development or so on an open source CFS-based software ecosystem for drones. We really like an interactive presentation, so if anybody has any questions during, please raise your hand, as we'd love to interact with you. So Windhover Labs was founded in 2015 with a mission to develop software that could be FAA certified to enable safety-critical drone operations beyond visual line of sight. We wanted to take years of space flight software experience and apply the principles and lessons learned to drones.
No, go ahead.
So in 2016, Windhover was awarded a Phase 1 Small Business Innovation Research Grant for the initial proof of concept. And then in 2017 through 18, we completed a Phase 2 SBIR and released the first version of the Windhover ecosystem. So I came in on the Phase 2 part. So this is really Matt's baby.
I was the Phase 1.
So we wanted to not only include software tools, but also provide a development process or workflow for contributors to follow. So we wanted to make sure that process was first in all this. Just flight software or even just the ground system, we could do a complete presentation on. So this is just going to be a high-level overview of everything we have available. And again, this is open source, so everything's available to use.
And we are going to have a demo at lunch over in the room over here. I think it's 102. We'll demonstrate the flight software, the ground system, and even if you don't have any interest in the drones or flight, if you do have any interest with CFS especially, I can you can have a look to see all the capabilities of CFS with the ground system that we'll have running hands-on. Okay.
So first, a little bit of our naming convention, our nomenclature. So Airliner is what we call the flight software, which is built on top of CFS. Commander is what we call our ground system. Pyliner is our scripting engine, which is made with Python. Trainer is our simulation and testing environment. Workshop is what we call our SDK. Hangar is our online portal. And CheckRide is our software certification process. So Airliner is 100% built on CFS. It is completely, it's at the wheel. It's driving the vehicle. There's nothing else involved. We have a couple of things, especially the scheduling, which I'm not sure if anybody else has done before. We'd love to hear about it if you have. But we're running really high rate threads of 250 to 500 hertz.
We've gone as fast as 1,000 hertz, but not actually in flight.
We are using 6.5, the open source release, but we do have multi-core support, and we also have faster than real-time support for testing, which I'll get into a little bit more later. So we chose CFS for its extensibility and widespread use for mission-critical space applications, which are, by nature, beyond visual line of sight. So all of these boxes represent CFS applications. I titled this chart as sensors and effectors. So this is input and output. The left-hand side is input into Airliner. The right-hand side is the output of Airliner.
And each one of these is one app in CFS. There actually are a lot of other apps, but these are the most important ones that you would think about for flight.
So the driver layer contains the minimal number of sensor applications for flight. If you wanted to move this to a different platform, you would just need to implement these core drivers. So that's radio control, GPS, magnetometer, barometric altimeter, gyro, and accelerometer. The sensors application combines various sensor data and can be used to implement voting or failover. So if you have duplicates or triplicates of any sensors, like triple IMU, you can implement your voting or failover algorithms in the sensors application. Estimators consume all the raw sensor data and estimate attitude and position for the top-level applications. The vehicle manager state machine controls mode switching, such as arming, disarming, manual, and position control. Navigator application controls autonomous modes, so return to launch or flying waypoints. Position and attitude controllers are pretty self-explanatory. Effector drivers mainly include motor controllers. Drivers we divided into platform-independent components and custom platform-specific components, which we thought was pretty important to easily port them. So the custom layer we tried to keep as thin as possible to also be able to exercise the maximum amount of platform-independent code, both through the simulation and in flight. Very.
Yeah.
Questions on this
Sure.
flight.
Go ahead.
Is your motor control, landing gear control, are they closed loop?
It depends on the platform, and the commercially available things that you can get, which is really what we focus on. It's open loop, so it doesn't have any feedback. But the Bebop though does have feedback, yes. And is that integrated in? Is there have we done any sort of integration to the feedback?
Not for the feedback, no.
Yeah, well, it's the Bebop. The port for the Bebop is not yet released anyway, so it's not done. But yeah, it depends on the platform.
And you mentioned voting, that I'm guessing you don't currently do any voting.
Yes, that's right. The phase 2 was not intended to be the certification of a vehicle itself. It was really just to get the minimum stack and the demonstration of the minimum stack. And so for the sensors, it's effectively just a pass-through.
Most of the time it's just PWM for motor controllers, and it's very unfortunate because you're just driving them and you get no feedback whatsoever.
Right.
So we also developed some additional applications. We have a video control application, which is streaming video built on top of Video for Linux, or V4L. We created an external application controller, which executes, monitors, and limits resources of external applications. We use this a lot with our Python scripting engine to actually manage the script that's running.
And it's actually running on the target. We have the capability of running the scripting engine on the target or off target.
All the standard CFS product line applications are available, of course. We also created a PX4 software bus bridge, which is a serialized bridge between our flight software Airliner, which is 32-bit, and other open source project flight software called PX4, which is 64-bit. So it makes running a mix of PX4 and Airliner applications possible. We have a custom CI application with two-step commanding, TO with prioritized queuing quality of service, and serialized channels for CI and TO with Google's protobuf.
The TO is for telemetry output for those that don't, or that haven't have worked with CFS. CI is for command and jet. Yes?
Can you talk more about the auto-generated protobuf serialization?
Oh, I could spend all day on that one, but I don't think we have any more slides on that. Actually, if you, I'm in the demo, I can get more into that, but essentially, we scrape the binary and we get the actual bit layout of all the fields, of all the messages in the downlink off the binary itself. So it just automatically adjusts for padding or for ABI or endianness, and then that then is used to feed into the ground system that's auto-generated, the scripting engine, which is auto-generated. So everything is built in Make. When you run Make, everything's all built.
Is that by parsing the debugging info, dwarf info, or how do you do that?
It's the dwarf section
Debug information,
inside the ELF. I think it's the dwarf section. It's the ELF image. Yeah, it's reading the ELF image,
Okay.
and then it's extracting the bit positions off the ELF image. And it's the only way I know of that is all definitive. Because if you read source code, that you aren't going to get the ABI or the padding off that. So it's always, if it's in the binary, it's always correct.
Thanks.
So version 1.0 of our ground system is built on top of YAMS, which is yet another mission control system, with Node as the front end. So all displays are built with HTML and JavaScript, which provides developers nearly infinite opportunities for customization. So any JavaScript library that you like, you can use it.
And this is version, this is 1, which is what we use for flight. The auto-generated one is still in work. It's functional, but we're polishing it now. And we'll show the version 1 and also the new version in the demo.
So yeah, we're demoing 2.02, right?
It'll be both, yeah. Yeah, I'll run that on mine.
So Commander proved extremely useful to us when we were trying to do sensor integration and checking out sensors during testing. So just here's a couple of screenshots of Commander 1.0. There's some gyro and accelerometer data.
And we watch this live in the flights. How are we doing on time? I think we're good. Anybody watching the time? I don't want to run late. Oh, okay.
Anything else you want to say about Commander?
No, not yet.
So we call our Python scripting engine Pyliner. We use it both on board and off the vehicle, so you can run it on the ground station, or if you want a more autonomous solution, it also runs on board the vehicle. Pyliner provides low-level access to all commands and telemetry on the software bus and includes a high-level API for common use cases. So if you want to fly waypoints, or just if you want to move up a certain amount or set a specific heading, that's all capable in the high-level API.
The low-level API, the API we use also for testing, and it has full access to all the software bus, or all the messages on the software bus, just because of the auto serialization. You can issue any command and you can read any data off the bus.
Yeah, go ahead.
So when you talk about the high-level API versus the low-level API, how is that distinction made? As in, for example, like does the high-level API actually generate several commands at the low-level?
The low level.
To the spacecraft?
Yes, yeah. So
yes, correct.
The low-level API is specific to CFS. Really, it has nothing to do with drones. In fact, it doesn't really have anything to do with CFS because the commands are just strings. It's just identified by strings, but it has nothing to do with drones. It doesn't. It's really agnostic of the fact that it's a drone. With the high-level API, it's all about the fact that it actually is a drone. I think this is an example of the high-level API.
Yeah, so we call our test vehicle Rocky because during testing it really took a beating and
Severe
kept on
beating.
getting back up. Which
where we do the test flights was about an hour away from where the offices are. So when in the very beginning, when the vehicle was damaged, we didn't want to lose the test day to go back and repair it. So you should have seen the repairs actually in flight or in the test with duct tape and zip strips and just enough to get it so it's vertical so it can launch.
So this is a high-level example of a waypoint mission. So this arms the vehicle. Takeoff is sort of an autonomous mode that allows you to reach, I believe, 10 meters off the ground.
For the beginning was 10 meters.
In position hold. And then current altitude is actually getting the actual altitude. And then you can add as many waypoints as you want. And that last function call actually flies the waypoint mission.
We should also note that there also is another, I guess it's an API for the Pyliner scripts if we're running in the faster than real time mode, so that it's in sync, so that it's in lockstep. The frame lockstep with the flight software, and that's useful for if you wanted to Monte Carlo or if you just want to run a lot of runs and you just didn't want to do it in real time. But in flight, that's not actually used.
So this is a low-level example of just reloading a CFS table. Is there anything you wanted to say about that?
We have a script that it just verifies that all the tables are reloadable, and we just run this occasionally.
So our sim is built on Gazebo. Each target has a corresponding software in the loop build. And we developed a tool called ARTI for headless real-time or faster than real-time regression testing. For example, you can set up Jenkins or whatever continuous integration you might be using to run a scripted flight in headless mode for continuous integration. And that's ARTI combined with PyLiner, of course, to actually script the flight.
Gazebo is also, it's used a lot in robotics. That's like the simulation of choice. And I should have added also for the Commander, the new version of Commander, it's got the capability of you can install modules or these plugins, and one which is in work right now is a ROS bridge. So you could use the flight software integrated in ROS, and everything is auto-generated all the way through.
So this is just a screenshot of Gazebo. We have a software development kit that includes Eclipse as an Oh, sorry, question.
The ROS stuff, you mentioned a ROS bridge. Are
Yes.
you saying you have a ROS bridge to your flight software, and then that ROS bridge talks to Gazebo, or is it
with the current version, it actually runs inside the ground system. So it's a bridge, but it's bridging the data that is from the flight vehicle that's going to the ground system that then bridged over to ROS. So that's where the bridge lies, but it's still the flight data.
okay? So there's no ROS bridge from the flight software itself; it's from the ground software.
In this version, there isn't, but there is one also in work that it actually would do the bridge on the vehicle itself.
Okay, thanks.
So we have Eclipse as our IDE and integrated debugger. And we have all the Vagrant provisioning scripts available for those that want to run natively. I should mention that Workshop is a Vagrant VM.
It's on the cloud also. It's on the Vagrant, the
Atlas, right?
Yeah, it's called Atlas. So it's installable with just one command. If you have Vagrant installed, it brings it down and it's already pre-configured.
So this is our online portal. We have documentation up. We have a source code exchange, issues and feature tracking, continuous integration, peer reviews, the scorecard, which I'll talk much more about in a second, for our process, and a support forum.
So this is the only part which we haven't really advertised yet. It's online, but it doesn't have as much content yet as I would like there to be. It takes a lot of work to get all the flight software, the ground system, the scripting engine, and also the portal online.
Okay.
Sure.
Let's go to the next slide, please. Thank you. So the scorecard is a process or workflow visualization tool we developed for our development process. Requirements, architecture, design, implementation, and test are linked for traceability analysis. The workflow transitioned through open, in-work, in-review, and baselined. Is there anything you'd like to say about scorecard, Matt?
No, but I'll also give a demo of scorecard and the portal in the other room.
And here's a screenshot of a couple of pieces of the scorecard. So all of these requirements up at the top are actually JIRA tickets as well.
Yeah, I think the first three are requirements. The next is the software architecture document, and then the design, and then it's unit tests. And it also has a date up there, so instead of just only like, you know, what's the status of this version, it's continuous. So you can say what's the status of the software, at this date and time, and you can see it there.
So all of these are actually baselined, but the blue bar at the top there would actually be multicolored to indicate the percentage of open, in-work, in-review, or baselined items for a particular application. Our current status is we're flying on Aerotena's OCPOC avionics board.
The Zinc version. We should have added that. Yeah, there's
Zinc.
a Zinc and an Altera, so it's the Zinc version.
As more of a higher end offering, so we're running that in both quad and octocopter configurations. We also ported to the Bebop 2 as more of an educational outreach option.
Which also doesn't work. Yeah, we should have mentioned that. There is a group of students that they're working on. It's like a tutorial of writing scripts and actually going through a mission. The
Typhoon is just in the simulated build, so we're not flying on hardware.
It ended up being that it wasn't very open. It was a closed. The architecture was closed.
We're in work on porting to the BeagleBone Blue board, and that's going to probably be more of a cost-effective option just because of the price tag on the BeagleBone Blue.
Yeah, I think the OCPOC is it's about 600, I think, and that's just for the avionics board. And then the Blue is 85, I want to say.
So for future plans, we'd really like to do systems engineering for redundancy and failure recovery. A big one is going to be RTOS support, either RTIMS, Zinami, or FreeRTOS. We'd like to do a web-based build and configuration tool. It'd be cool to have like drag and drop capability for a lot of things. So you could just say, I have this particular sensor or this GPS unit, and I drag and drop and say, okay, that's the GPS I've selected, and the build system will automatically build the software for you.
The build system right now is based on CMake. It's not the Ames one. We started on the CMake well before the Ames one was available. So we continued with that.
We'd like to do a sensor integration for the Intel RealSense camera or Aerotena's 360 Sense and Avoid radar. We'd also like to do a standards-compliant mission planner and, of course, more platforms. We'd love to do a fixed wing as well because we're only on multi-copter configurations at the moment.
Yeah, in fact, the architecture is all designed so that in order to go over to the fixed wing, it's really just the two applications have to be replaced. That's the position control and attitude control. All the rest of it, though, is the same.
So we think CFS for drones makes a lot of sense. If you've worked on a drone project with CFS, we'd be really interested to talk to you about it. And if you have any questions.
Or CFS in general, I guess.
Or CFS in general.
Yeah, I've been working with CFS for the past 4 years, almost 5. Yes.
Have you had any occasion to work with DoD systems? I know you mentioned NASA, so you probably haven't bumped up against the DoD rules about flying right now. And do you have any future plans on security?
So it is interesting you brought that up because I know it's been about a year now that the Digi drones were grounded because of an issue with security, and that was DoD said you can't use, and I guess there was almost 80,000 drones which were grounded that they aren't allowed to use anymore. We haven't done anything with DoD because we just don't have any contacts with them, and there hasn't really been a lot of work with security because in fact, it was mentioned, I think it was yesterday about that inside CFS it's assumed to be trusted. So any sort of a protection is is going to have to be a layer on CFS, but that would be future work that we would add to the comm layer, which right now is Wi-Fi. Well, for the platforms which we support at the moment, it's Wi-Fi. Yes.
So I'm just wondering, in robotics and in drones, they use ROS a lot.
Yes.
And I was just wondering how CFS compares to that. I mean,
okay.
In your experience, because I haven't seen CFS
I've actually worked on a project where they it was a drone, and I wanted to go with CFS. They went with ROS because they were all robotics people. It would be extremely hard pressed to do any sort of a in my opinion, to do any sort of a certification at the level which we do for flight software in ROS. You don't have the same level of determinism. It's also a lot more of a CPU hog because everything's all distributed. It's supposed to be it's multi-platform, but it seems to only work in Ubuntu. Other things, but I think if you're just doing a one-off in a laboratory and you just want to get something that's real quick, and you're a roboticist, then yeah, ROS is probably the best way to go. But if you're actually if this is going to be fielded and it's leaving the laboratory, you should probably go with something which is much more hardened like CFS. But the ROS has an extremely large ecosystem, which is one reason why they go with that. Probably the biggest reason why they go with that.
There is an effort for ROS-M from the Tank Command.
And what?
There's an active effort for ROS-M, which is like a variant, I think, of ROS-2 to target what the Tank Command needs. And Mark over at the OAR booth works with them so he can answer any questions about that, because at least the Army, the field vehicles recognize that they can't field something based on ROS, but they've got a lot of prototypes based on ROS that are unsuitable to field.
Right. I think you have a question. Did you have a question? Oh.
So your customer base, is there anything you can say about your customer base?
Is there anybody who wants to buy some flight software for drones? When we started this, it was the market was very interesting. It was really hot. It still kind of is, but it kind of slowed down. But we were targeting manufacturers of drones. So like we wanted to be the Android, like what Android is for cell phones, we wanted to be for the drones. But the big thing which ruined it for all of us is actually Airware. I don't know if you know about the company called Airware. They got their investment extremely early, a lot of money. It was like 160 million. They spent it all, went out of business a month ago. We bought a few of their drones real cheap, but they really kind of ruined it for the venture capitalists. So right now everybody's waiting to see what the FAA is going to do.
Okay.
Yeah, so now we're focusing on inline engineering right now.
All right. Thanks a lot, guys. Very interesting, kind of a different approach.